Good evening. Good evening, and welcome. Welcome to Perimeter Institute here in Waterloo, Ontario, Canada, and welcome to this Perimeter's Public Lecture Series. My name is Greg Dick, and it is a pleasure to welcome those of you here in the theater and to our online audience. And first, before we begin, in the spirit of understanding and learning from what has come before, Perimeter respectfully acknowledges that we are located on the traditional territory of the Attawadran, the Anishinaabe, and the Haudenosaunee peoples. Perimeter is situated on the Haldimand Tract, land promised to 6 nations, which includes 6 miles on either side of the Grand River. And for those of you watching online, you can follow us on social media. We're at Perimeter and use hashtag #PILive. And you can follow and engage in conversation with scientists behind their keyboards during the talk. And if you want to send questions to me, use hashtag #PILive as well. And I'll have those questions ready to go for our presenter at the end. And now it is my pleasure to introduce tonight's very special guest speaker, Dr. Bryan Gaensler. Dr. Gaensler received his PhD from the University of Sydney and subsequently held positions at MIT, the Smithsonian, Harvard, and Sydney before taking his current role as the director of the Dunlop Institute for Astronomy and Astrophysics at the University of Toronto. As the director of the Dunlop Institute in Toronto, Professor Gaensler aims to develop new approaches to astronomy while also training the next generation of astronomers. He is a Canada Research Chair of Astronomy at the Department of Astronomy and Astrophysics at the University of Toronto and the director of the Canadian Initiative for Radio Astronomy Data Analysis. Dr. Gaensler is co-chair of both the Canadian Astronomy Long Range Plans 2020 and the Toronto Initiative for Diversity and Excellence. In his spare time, he co-authored 400 scientific papers on cosmic magnetism, neutron stars, supernova explosions, and interstellar gas, and wrote a popular astronomy book called Extreme Cosmos, which has been translated into 6 languages. Tonight, Dr. Gaensler will share the latest thinking on interstellar travel and the search for alien life, and how the research may be even more exciting than the stories in our imagination. Ladies and gentlemen, please welcome Dr. Bryan Gaensler.
Thank you so much for that welcome, Greg, and thank you to all of you for coming out here on this chilly night. It's such a pleasure to be here. As you've heard from Greg, I've had the privilege to work all over the world, and let me assure you that the Perimeter Institute is something really unique and really special. We are so lucky to have this place here in Waterloo and here in Canada, and I'm thrilled to have been invited and to have a chance to tell my story here. So, So the very short version of my talk, for those of you watching later on YouTube who don't want to sit here for an hour, is that warp drive and aliens. Well, I'm gonna give you a spoiler. We don't have warp drive yet, and we haven't found the aliens yet, but there are very exciting prospects for the future. If you love science fiction, then be patient, and you will see your wildest dreams hopefully start to become real. So, I'm an astronomer, and I love saying those 3 words. So I'm going to say it again. I am an astronomer. And I love saying that because I decided that I wanted to be an astronomer when I was about 5 years old. And I've never wanted to do anything else. And if I could go back in time to that 5-year-old and tell him, guess what? You got to be an astronomer, and it really is awesome. I just cannot imagine how happy that would make him feel. So it's the only thing I've ever wanted to do, and it's just a thrill to know that I am getting to actually do that. So why did I decide to become an astronomer? Well, my parents bought me a lot of books. I love to read, and it kept me quiet. So they bought me lots of books. And I love the books that my parents got me. They got me books on dinosaurs and books on volcanoes and books on race car engines. And I just devoured them. And I love the fact that they all were full of facts and they had answers to everything. But then they got me this book that was quite different. This book here, I still have this book, The Album of Astronomy. And this book just totally changed my life. Because while all the other books were full of answers, and that was great because I liked learning about these things, this book was different. Instead of having answers, it was full of questions. It was basically saying, we don't know what is going on in the universe. There are so many mysteries and we just cannot figure it out. And this was incredibly exciting to me for a few reasons. First, until that point, I was only 5, I thought that there was no such thing as a question that people did not know the answer to. That like humans, someone would know the answer to everything. So I figured that that my parents probably knew pretty much everything. Of course, when I was 15, I knew that was totally wrong, but at 5, I thought they did. And if for some reason my parents didn't know the answer, then my teacher would know the answer. And if unimaginably my teacher did not know the answer, then back in the 1970s, we had these things called libraries and encyclopediae, and I could look it up in an encyclopedia and the answer would be there. But what this book told me is that there are some questions that nobody on the planet knows the answer to. And that blew my mind. But the even better thing is it said, but there are these people who figure out the answers to these questions, and they're called astronomers. And these astronomers take things from the we have no idea column, and after a lot of hard work and brilliance, they move them into the, oh yeah, we know what that is column. And I thought, oh my gosh, that is what I want to do. What's great when I look at this book now, 40 or 45 years on, is that the big mysteries, we would give both our arms to answer the answers to these question mysteries of the 1970s, are now just mundane things. The answers are in every textbook. These are not even remotely mysterious anymore. All of those big mysteries have been completely answered 40 years on. But now we have these huge mysteries in astronomy, like what is dark energy, what are fast radio bursts, these massive mysteries that, we didn't even know what the question was back then. And now they're huge mysteries in astronomy. And so I love the fact that we go from answering a question to asking a question, to answering a question, and then coming up with totally new questions. And this process is happening all the time. Just to prove to you about what a hardcore astronomer I was at a very early age, I'm going to show you a picture from about 1980 when my parents and I went to the equivalent of the Canadian National Exhibition. I grew up in Australia, so we obviously didn't have the Canadian National Exhibition in Australia. Instead, we had something called the Royal Easter Show, which is pretty much the same sort of thing. And there was a cartoonist there who said, I will draw a caricature of you for $5. And I said, oh, Mum, Dad, please, can I have $5 to have a picture drawn of me? And they said, okay, here's $5. And I sat down with the cartoonist, and they said, why don't I draw you doing what you're going to be when you grow up? What do you want to be when you grow up? And I guess they're expecting me to say firefighter or airline pilot or all the usual things that little kids say. And I said, I want to be an astronomer. And she said, okay. And she drew me as an astronomer, and here I am. So you can see that I look exactly the same. The only difference now is that my telescope is a whole lot bigger. But I'm very fortunate to still have this cartoon from all these years ago because it reminded me of just how passionate I was about astronomy back then, and nothing has changed. So I love being an astronomer, and I love astronomy, but the only other thing that matches my passion for astronomy is my passion for science fiction. So science fiction is a bit of a touchy topic for astronomers. I'm going to grossly generalize here, but half of astronomers love it and half of them hate it. And the reasons why they love it and the reasons why they hate it are exactly the same. It's because it breaks the rules. So astronomy is part of physics, and physics has these beautiful laws that explain everything from a butterfly to a distant star, all follow the same rules. So some people really don't like science fiction because they say, look, I've spent decades training to understand these rules. You can't just go off and then make a movie where you just cheat. And other people love science fiction because, look, I spent all day at work strictly following the rules. When I get home, I just want to let my hair down and break some rules. And so I fall in the latter category. I love science fiction because I know that most of the things in science fiction are impossible and they break the laws of physics. But it's just the rebellious part of me saying, what if? But apart from that, there's two reasons why I love science fiction. The first is that, in a very profound way, science fiction casts new light on what it means to be human. If you read a good book or watch a good movie, not a science fiction story, but just a normal movie, often the reason why it's enjoyable is because you're seeing how human beings react to complicated, emotional, challenging situations. And science fiction takes that to another level. It puts humans in situations that could never happen in The Crown or Downton Abbey, but far more futuristic, complicated situations that we're never going to experience in everyday life, and you can ask, how do people respond to that? So this is one of my favorite movies of the last few years, the movie Arrival, and so Amy Adams plays a linguist, and she is reacting in this very complicated way to the fact that she has encountered aliens who look and think completely different from us, and she's trying to work out how to communicate to them. If you haven't seen this movie, it's a very good movie, a very powerful, emotional movie about being a parent and about memory and about life and death, but it's all in the context of aliens landing and trying to talk to us. And the questions that are asked in this movie are not questions that you could answer in just a contemporary piece set in Waterloo in the year 2020, unless you bring in the aliens. So I love science fiction because it allows us to ask important questions about the human condition. And the other thing I love about science fiction is a lot of it is about technology. And as we know, technology changes our lives completely in many complicated ways, and it's going to continue to do so. And so science fiction steps forward maybe 5 years or 10 years or 20 years and asks questions ahead. How are these new technological changes going to change our life for better or for worse? So here's another recent science fiction show, Westworld, where there are these high-tech robots that are basically indistinguishable from humans, and it explores in a very complicated way, what does it mean to be a living thing? What does it mean to have emotions or feelings or thought? And, can robots be sentient? So these are questions that we'll probably have to address in real life in 10 or 20 years, but science fiction lets us ask those questions right now and prepares us for the future. So there's fact, and there's science fiction, and some people think that they're completely separate and they have nothing to say about each other, and I'm one of those people who thinks that they're very intertwined. So if we even look up what astronomers are talking about and thinking about, it can get a little bit hard to tell the difference between science and science fiction. So let's look at some of the highlights of my field of astronomy over the last couple of years. So one of the, who could have thought this could possibly have happened moments happened about 2 or 3 years ago when we had the very first interstellar visitor from another star that we've ever been aware of. It wasn't aliens, but not the sort of visitor we might hope for. It was a rock, an asteroid, and that drifted past the Earth, and it caught attention because there are lots of asteroids that we see all the time, but they're all orbiting the sun. And this one was at a very severe angle and a very high speed, such that it can't have been in orbit around the sun. It was coming from somewhere else. And it approached the sun at very high speed, whipped around due to the sun's gravity, and then zoomed off out into interstellar space, never to be seen again. We gave it the name Oumuamua, and we believe that this rock used to be an asteroid in some other solar system, maybe on the other side of the galaxy, and for tens or hundreds of millions of years has been whizzing across the galaxy, and just by sheer luck happened to drift into our solar system before flying off again. So that alone is amazing. The first time we've ever seen any object come into the solar system from outside the solar system. But what's more, when we measured its shape, it wasn't like a normal asteroid. Most asteroids are sort of lumpy, vaguely round with sort of lumps and bumps on them. But you can see here that Oumuamua was very different. It was more shaped like a cigar. It was dark and extremely long, about 10 times longer than it is wide. And that's a very strange shape. So a lot of scientists were saying, who could have thought of this? This is like beyond science fiction. But if you're a science fiction fan, you know that this is not beyond science fiction. We've seen this before. Probably the most well-known time we've seen this is in the movie Star Trek IV, The Voyage Home. That's the one where they go back to the 1980s and save the whales. But this, indeed, exactly like in real life, a dark, cigar-like alien probe comes from outside the solar system and travels to Earth, an interstellar visitor that looks remarkably like Oumuamua. And even Star Trek wasn't the first to come up with this. Back in 1973, Arthur C. Clarke wrote a novel called Rendezvous with Rama, one of the great science fiction novels of all time. They haven't made it into a movie yet, but they really, really should. And in this one, the plot is remarkably similar to real life. A cylindrical, dark asteroid comes flying in from outer space on a very severe orbit and swings around the sun once and then flies off. Before it does, they check it out, and it turns out that it's actually an alien space probe. So Oumuamua is not telling us to save the whales, and it's not an alien space probe, but it's remarkable how science fiction actually anticipated the idea of this dark, strangely elongated interstellar visitor. So, all right, science fiction beat us to the punch on that one, but come on, like there's been so many discoveries lately, there must be other ones that completely blow science fiction out of the water. So one of the unquestionable discoveries of 2019, in fact, most science magazines rank this the #1 breakthrough of 2019, was a spectacular image of a black hole. So this is not an artist's impression or some clever sort of computer overinterpretation. This is an actual picture of a black hole, and it was people here at the Perimeter Institute, Avery Broderick and others, that were absolutely instrumental in making this image. So this is a black hole. It's 55 million light years away. The sharpness of vision here is ridiculous. It's the same sharpness of vision that if someone was sitting in New York reading a newspaper and you were in Paris, this sharpness of vision is the same as being in Paris and having a telescope good enough to read a newspaper in New York. So it's a really remarkable breakthrough. You know, it doesn't get any better than making an actual picture of a black hole. But it won't surprise you, that, I think, no offense to our hardworking scientists here at the Perimeter Institute, but the black holes in science fiction, they look much better than this. Has anybody signed up yet for Disney Plus? Like, hands up, have you joined Disney Plus, anybody? A few of you? Have you yet watched the classic, brilliant piece of art, the 1979 Disney movie, The Black Hole? Has anyone watched that? I saw it when it came out in 1979, and I watched it a couple of weeks ago again, and you know what? It's still a pretty good movie. So here is a still from Disney's The Black Hole. Go out and watch it if you can. This is before Disney had the budget they had now. This is actually a pool of water being stirred in a plexiglass tank with dye added to it. But even so, I said no offense, but it actually looks better than the real thing. But that's actually not what black holes probably look like. What you're seeing here, if you could crank up the resolution even more and make a sharper vision, which is what astronomers are now trying to do, is you'd see something like this. So this is a clip from Interstellar, and this was based on actual astronomical calculations made by Nobel Prize winner Kip Thorne using a supercomputer of what a black hole would look like up close. All right, so that's Matthew McConaughey about to narrowly avoid destruction in a black hole, but with almost no artistic license at all. That's pretty much what a black hole really looks like as far as we can tell, and in the coming years we'll get sharper and sharper pictures of the real thing, and it will start to look like that. I guess one big difference between science and science fiction is how we name things. This object's name is M87 star, and the one here is called Gargantua. So I don't know which black hole you'd rather be sucked into, but I'd far more like to dive into Gargantua than I would into M87 star. Okay, so clearly science fiction has thought of everything, but I did think of one thing that, to the best of my knowledge, has not been anticipated in science fiction. There might be some science fiction fans here in the audience or online, and if you know of some sci-fi that predicted this, then please let me know. I'm happy to be corrected. But in August of 2017, something remarkable happened involving things called neutron stars. So neutron stars are some of the strangest stars in the universe. They weigh more than the mass of the sun, but they're only the size of Kitchener-Waterloo. They're like 25, 30 kilometers across, but they weigh more than the mass of the sun. So they're some of the densest objects in the universe. And if you think one neutron star is pretty incredible, well, imagine two of them orbiting each other and then crashing into each other. And that's what we saw in August of 2017. So here's an artist's impression of what we saw: two neutron stars spiraling in faster and faster, and then eventually coalescing, possibly forming a black hole, and creating a spectacular explosion. And while we didn't see the moment of the explosion itself, because we didn't know it was about to happen, this explosion actually was so violent that it made the entire universe shake. It's like the granddaddy of all earthquakes. So our universe is a mixture of space and time, space-time, and the actual fabric of space-time itself vibrated across the entire universe when these two neutron stars merged. And we actually felt that happen. You and I didn't feel that happen. You weren't sitting there eating a sandwich on that day and think, oh, what was that? But we have, the vibration was tiny. It was like smaller than the diameter of an atom. But we have these incredibly sensitive instruments, one in Washington and one in Louisiana, called LIGO, and they detected the vibration from these two neutron stars merging, and literally the entire universe shook for a few seconds after that, which is quite extraordinary. And as I said, I'm pretty sure that this is one thing that didn't turn up in science fiction before it happened in real life, but if you know better, I'd be happy to be corrected. Okay, so science fiction is normally ahead of the game, and given that my talk is on warp drive and aliens, it's not going to be a shock to you to tell you that science fiction is ahead of the game here too. So, warp drive is really all about traveling from one place to another quickly. We know that stars are unbelievably far away. The nearest star to us is 40 trillion kilometers away. So, getting from one star to another is not super practical. And in science fiction, you sort of want people to be able to go to other stars, to travel around and have adventures, so you have to have some cheat, some way of getting from one star to another. And normally, science fiction doesn't worry about the details too much. They just invent warp drive or hyperdrive or something, and that's just a convenient way of getting from A to B. So in the movies, it's super easy to travel from one star to the other. So here's a scene from Return of the Jedi, Admiral Akbar, may he rest in peace. And here we go, traveling from one star to another.
All right, stand by.
So easy. And they pop out 2 seconds later and they're at another star system. So of course, in real life, I'm not giving away anything to tell you it's not that simple. So if we want to be able to live the life of science fiction and travel to other stars, how might we actually do it? So old school science fiction is you have a rocket ship. So here's a real rocket ship, and here's a science fiction version. Could you build a rocket ship and use it to travel to another star? So the short answer is not really. The way the space shuttle worked is it's full of fuel, and you light that fuel, and you get a massive explosion. You direct the explosion out the back, and the gas flows out that way, and you get a reaction. If you push the gas out that way, you go that way. Okay, so it's very simple, brute force technology, and it pushes the space shuttle up into space. Now, the space shuttle is really, really big. Who's actually seen the space shuttle at one of the museums? Anyone seen it? It's huge, right? And have any of you been to the one in Florida where they actually had the boosters as well? Anyone been to Cape Canaveral? These boosters are even bigger than the space shuttle. So you get a feeling you've got this massive multi-story building just full of rocket fuel, and that's what you need to launch the space shuttle. But the space shuttle, and this is sort of a bit embarrassing because it's not really a space shuttle. It barely goes into space. The space shuttle only went up 300 kilometers. That's not even from here to Ottawa. So it's a very short distance. And that you needed all this incredible fuel just to get 300 kilometers above the Earth's surface. So you still haven't even escaped from the Earth's gravity, let alone escape the sun, let alone travel to another star. So even if you could build a rocket that had everything you needed on it to travel to another star, and you built the fastest rocket that's ever been built, it would take about 20,000 years to get even to the nearest star. So not only does that not make for great TV on a science fiction movie, it's obviously not very practical. If you want to travel 20,000 years, that's many, many generations. You're going to need thousands of people and food and radiation shielding and schools and all the rest of it. You're going to have a spaceship the size bigger than a cruise ship, and that's just not practical. If you really cut everything down to the bare minimum, the calculations have been done that you could build a very small, hyped up, superpowered rocket that could get to the nearest star in 900 years. That's still a pretty long time. And there's a few problems with that. Firstly, that's to get to the star, but of course, you're traveling very fast when you get to that star, and you've used up all your fuel, so you have no way of slowing down. So you finally get to the star, it's like, bye, and that's the end of that. So not very practical, but even that would take 900 years. And what's more, you'd need more matter than there is in the entire solar system to do it. And so you can imagine how big the rocket boosters would have to be. So while I love pictures like this is just simply never going to be a practical way of traveling between stars. Just the amount of fuel you need is just completely impractical. So let's look at options that don't require so much fuel. There's another alternative called the ion drive. It sounds like science fiction, but it's actually real, and it simply involves using electricity, like a battery or something even nuclear-powered or solar-powered electricity to slowly evaporate a lump of fuel and gently blow out your fuel at the other end. So you use much less fuel, but you shoot out the individual ions much, much faster. And so this is an artist's impression of a satellite probe called Dawn that was used by NASA, and it visited two asteroids, Vesta and Ceres, and it traveled 6.9 billion kilometers over 11 years. And it traveled that 6.9 billion kilometers using only 400 kilograms of fuel. So that's nothing. Like, that's just a big block of fuel about this big. It used xenon, so just a big tank of xenon gas weighing 400 kilograms, which is not that much compared to the space shuttle, and that's all it needed to travel billions of kilometers over 11 years. And if you think that sort of looks too good to be true, like this just looks like it's artistic license and there's nothing really like that, here's a photograph of an ion drive in the lab, and it looks exactly like the artist's impression. So these things actually work, and there have actually been many satellites now that have flown around the solar system using these ion drives. The problem with the ion drive is that it's really, really weak. It's a very gentle thrust. So if you're shopping to buy a fancy car, a Porsche or a Lamborghini, it might be important to you to know how fast it takes to go from 0 to 100. The most expensive cars that you can buy these days go from 0 to 100 in a little less than 3 seconds. So if you walked into the showroom and pointed to NASA Dawn and said, what can I get out of this baby? Well, the answer might disappoint you because it goes from 0 to 100 in 4 days. So the acceleration is really, really weak. It takes a long time to get up to speed. So that's the price you pay for not having to need much fuel, is that you don't get a lot of oomph out of it. And so if you tried to use the ion drive to travel to another star, even to the nearest star, it would take you 80,000 years to get there. Again, not very practical. There's another problem. As I said, the ion drive is super weak, so you could not put this thing on the ground and say, ready for takeoff, 3, 2, 1, go. Nothing would happen. It's too weak to escape the Earth's gravity. So you still need all of those rocket boosters to get it out of the Earth's orbit, and only then can you turn on the ion drive. So this is probably not a very practical solution either. What about if we get rid of the engine completely and use an energy source that isn't attached to the spacecraft? Could this solve our problems? So this has been thought of too. It's been around in science fiction for a very long time, and the idea is to use what are called solar sails. And the theory here is that the sun actually is blowing off this gentle wind in every direction, the solar wind. It's traveling at quite a high speed, these flow of particles in every direction. So as long as you want to travel away from the sun and not towards it, you simply have to unfurl a big sail, and it will fill up just like the sail of a ship, and you'll be blown away from the sun. And just like a sailor, you can use various tricks, tacking and all the rest of it if you don't want to travel directly away. So here is a solar sail being used by Count Dooku in Star Wars Attack of the Clones, and here is sort of the classical old-school 1950s science fiction version of a solar sail. So could we use a solar sail to sail out of the solar system on the sun's wind? And the answer is, well, maybe. There's also, remember the problem I mentioned before is having to slow down when you get to the other star? Well, it's perfect. You use the sun's solar wind to sail halfway to the star you're going to, then you turn the whole thing around, and you use the wind of the other star to slow down, and then you go to a gentle stop when you want to go there. So people are actually working on this technology. Here is a spacecraft called LightSail 2 that was developed by the Planetary Society. The space probe itself is really, really tiny. It's just in there. It's only about this big. But the sail is huge. It's about 30 square meters, or about 350 square feet. So this thing was actually launched about 6 months ago. Here it is. This is a photograph from the probe. So you can see this is Baja, California down here in Mexico in the United States. This is the probe, and here is the actual solar sail unfurling. So this was in June of last year. So, of course, the big question is, does this actually work? And the answer is, yes, it does. So they unfolded the sail, and they measured whether the sun's wind actually pushed this satellite into a new orbit. But the results are not exactly spectacular. So this is before they unfurled the sail. It was 725.6 kilometers above the Earth's surface. They opened the sail right here. Not much happened for a few days, but then very gently the solar wind pushed it to 727 kilometers above the Earth's surface. So this is the first time anyone's really done this, and it did work. It raised the orbit of this spacecraft by 1.8 kilometers. You've got to start somewhere. So clearly we have a very, very long way to go here. There's lots more technology we have to develop in order to be able to use solar sails. And the sails are going to have to be much bigger. They're going to have to be hundreds of kilometers across. And then you have the whole technological problem of how do you pack the sail up when you launch the thing? How do you unfurl it? How do you spin the thing around? What happens if like a meteorite rips a hole in it? There's all sorts of huge challenges. But if you can work out how long it would take to get to near a star using solar sailing, and the answer isn't actually too bad. It's only 75 years. Now that's still a long time. It's, you're not going, if you start as a young man or woman at the beginning, you're probably not going to be alive at the end of it. But 75 years, we're actually starting to get into the right ballpark. Unfortunately, there's really no way to go any faster. You can't, crank up the sun or crank down the sun. The sun is the sun, and it gives out wind at a particular speed. But there is at least a way that, is not complete science fiction, because it works over 1.8 kilometers. We just have to get it working over 40 trillion kilometers, and we are in business. And we can travel to another star using no fuel at all in 75 years. But maybe we should be thinking outside the box and thinking a bit harder. Well, there are some other options. One that comes up a lot is this idea of something called the EM drive, or the Mach effect thruster. Did anyone see this show last year, Salvation? Anyone see this? You're probably not admitting you want to see it because it was really bad. Filmed here in Toronto, though, and there was a lot of technology in it, and one of them was this idea of this EM drive. And the idea here is a little bit hand-wavy. You inject microwaves into this cavity, and they bounce around, but they bounce out fast, slightly faster at one end than the other, and you get a tiny amount of thrust. The only problem is that the laws of physics say that you can't get something for nothing, and most people, including me, think that this breaks the laws of physics. People have claimed that it does produce a thrust, but other people have rebuilt the same experiment and haven't been able to produce it. So this is probably complete fiction. But if we can somehow get this to work, then it does perhaps, maybe, if you don't mind breaking a few laws of physics, produce a tiny, tiny, tiny amount of thrust. So, can this go fast enough? No. Does it work? No. Does it obey the laws of physics? No. But you never know. Okay, are there other options? Again, let's think outside the box. Maybe you shouldn't travel there at all. Wouldn't it be easy to get to another star if you simply look at me, you break me up into pieces. I've got an arm and some hair and some feet. You pack all that up, you transmit that information to the other star, and then you put me back at the other end. That's all an email is, right? I mean, if I send you an email, the keyboard doesn't get sent over to you. The computer records what the keystrokes are. It remembers the order I typed them in, and it puts back that information at the other end over the internet, and you get the message that I sent you. So, this has a technical name. It's called teleportation. And maybe this is a way to get from one star to another. So no rocket fuel is needed at all. You just have to break me apart into pieces and beam the signal and put me back at the other end. And of course, this has been a staple of science fiction since forever. And of course, the most famous example of teleportation, of course, is in Star Trek. Okay, so in that case, they probably only teleported over a few hundred or a few thousand kilometers, but if it works over a few thousand kilometers, why can't it just work from one star to the other? So the good news is that teleportation is real. The bad news is at the moment we can only teleport one atom at a time. But it is real, and it's called quantum teleportation in real life, if you want to look it up. And the record for teleportation at the moment, involving one atom, is teleporting over 1,400, over a distance of 1,400 kilometers. It was a Chinese satellite called Mikius, and they teleported an atom from the ground up to the satellite. So the actual atom never moved. All you do is you take one atom and you measure its exact properties, and in the process of measuring its properties, you actually mess it up and you lose that information, but you can transmit that state to the spacecraft and you can recreate an atom exactly the same. So the atom at the end is indistinguishable from the atom at the beginning. To all intents and purposes, it's teleportation. And it turns out to be really useful. It's really important in cryptography and sending uncrackable signals, which is very important in finance and banking and all the rest of it. But can this be used to teleport humans? Well, probably no, and probably not ever. There's a few catches to this in terms of using it for interstellar travel. The first is that you need a receiving station. So you've got to get your receiving station to where you want to teleport to first. So if you want to visit the nearest star via teleportation, you've got to get the receiving station to the nearest star first, and then you go back to all the problems I just discussed. That has to get there through the normal means. But once you've done that, you're in business, and you then just simply have to scan every aspect, every atom of a human being and transmit that. And that's a bit of a problem, because you can calculate just how much data you need to describe a human being, an exact copy. You really want it to be exact copy, right? You don't want to teleport there and discover something important missing. So the amount of data you need to scan one human is 300 million trillion gigabytes. That's 3 with 32 zeros at the end of it, gigabytes. So that's a lot of memory sticks. And then if you work out, well, okay, now you have to transmit with a radio signal, you have to actually send that signal to that star. At the highest data rates that we have at the moment, it would take you 5,000 trillion years to transmit that information, which is 360,000 times the age of the universe. So it would actually be quicker to walk to the nearest star than to teleport. So I'd say there are significant barriers to teleportation. It does not violate the laws of physics. Unbelievably, it doesn't. We can do it. But the practicalities of transmitting even a single human being are absolutely enormous. So I don't think we'll be teleporting anytime soon. All of these methods also suffer from something else. And that's another catch, is that you can go really slow, and it can take you 1,000 years or whatever. If you could figure out using one of these methods going really, really fast, suppose you could build a rocket ship that could travel at half the speed of light, or 80% of the speed of light, or 90% of the speed of light. You'll get there faster, but you then have another problem, and that's something called time dilation. It's a consequence of Einstein's special theory of relativity. And what it says is that when you go really fast, your clock runs slower than the rest of the universe. And time dilation hasn't come up too much except in really super nerdy science fiction, so you have to dive really deep to find it until Matthew McConaughey came along and saved the day, as he always does. In the movie Interstellar, we see time dilation. Matthew McConaughey has a young daughter. He goes off, gallivants around the galaxy and visits black holes and all the rest of it, but despite being an advanced NASA astronaut, didn't seem to know about time dilation. He must have been sick that day, because he's rather surprised when he comes back to Earth, and a month has passed for him, he's still gorgeous, and his young daughter is now an old lady. And so this is a real effect. We have demonstrated this with clocks, flying clocks at high speeds, comparing to clocks on Earth, and they're very slightly different. So even if you traveled, say, at only half the speed of light, which you can go a lot faster, it's like a 15% effect. So if you were away for, say, 10 years, everyone on Earth would be away for 12. But if you want to get somewhere fast, say if you want to go at 90% of the speed of light, it becomes about a factor of 2. And if you want to go at 99% of the speed of light, it becomes a factor of 7. So if you went on a journey to other stars at 99% of the speed of light, then you might think you're away for 10 years, and when you come back, 70 years have passed. So all your friends have aged or died, technology is completely different, society is completely different, you're a total fish out of water. So if you're given the chance to go on interstellar travel at high speed, it might be the trip of a lifetime, but it's going to be very lonely and confusing and strange when you come back. Maybe there's one way around all of these things, and that's, of course, in the title of my talk, warp drive. So warp drive is a staple of science fiction, and we saw it in the Star Wars clip that I showed at the beginning with Admiral Akbar. But it was also a valid scientific idea. And so the idea was developed by a Mexican physicist, Miguel Alcubierre, and he is a science fiction fan, but thought about, how could you actually do this in real life? And the idea is that space is actually can be stretched and squashed. I can't do it just with my hands like this, but under the right conditions, you can stretch and squash space. And you can use that to actually move from one place to the other without using any rocket fuel at all. So the idea is that suppose I have a big rug, and I put a toy car on my rug all the way over here. And I want to get that toy car over to me standing over here. So one way I can do it is I can walk over the toy car and I can hold it and I can wheel it across the rug to me. So that is like a rocket ship using up fuel. But there's another way I can do it. I can put the toy car on the rug over there, and then I can just grab the rug and I can bunch up the rug and pull it towards me, and then the car will eventually get to me. The car, as far as it can tell, has not moved at all. The wheels have not turned, it hasn't had to use any energy, and yet the car has traveled from over there to over here. And that's exactly the idea behind warp drive, except it's using actual space instead of the carpet. And so the idea is you have some sort of spaceship. It doesn't have to use any fuel at all, but if you squeeze the space ahead of it and stretch the space behind it, you can actually move it from one part of the universe to another, in principle as fast as you want, without using up any fuel. Now, of course, you have to use energy, but the energy doesn't have to actually be on the spaceship. So this is, in principle, a way of traveling to other stars without having to worry about time dilation or huge amounts of fuel or anything. There's only one small problem. We have absolutely no idea how to actually squash or stretch space-time. And if we did, it would require more energy than all the energy on Earth put together. But other than that minor detail, this is theoretically possible. And, if something is theoretically possible, what do they say? Where there's a will, there's a way. Maybe thousands of years from now, the Alcubierre drive will become reality. Okay, so this has been a bit of a downer. I've told you all the ways in which we will never visit other stars, but all hope is not lost. I'm going to finish this part of my talk by telling you one way in which we really might be able to visit other stars. And this is a program that is a real program that's in its early days. It's probably only about 5 or 10 years old, called Breakthrough Starshot. And what Breakthrough Starshot says is, let's forget humans traveling to other stars. That's not going to happen anytime soon. And let's forget sending some giant space probe to another star. But what if we had a space probe that was only this big? If you have a space probe that's only like, the size of a grain of rice, then it doesn't need much fuel at all to get to another star. You can actually get it going quite fast in lots of ways. And of course, the best sounding way, and the way they're proposing to use it, of course, is using giant space lasers. So the idea is you have your giant space lasers. Here they are. All ready to shoot their laser. And then somewhere above in Earth orbit, you have a tiny little spacecraft, which is right at the center here, with a big sail around it. And then you fire up your space lasers, you aim them very, very carefully, and you focus them all to exactly the right spot, and they hit the sail, here we go, and accelerate this tiny little probe up to enormous speeds, up to 20% of the speed of light, or about 60,000 kilometers a second. At that speed, you can travel to the nearest star in 20 years. You can't slow down, but you fly past that star at great speed. You've got just a few minutes to take a few snapshots. Hopefully they're in focus and you're pointing in the right direction. And if there's a planet there, then you get a couple of snapshots and you beam them back to Earth before flying out into the void forever. So it's not the same as being there, just getting a few postcards, but it's better than nothing. And this is perhaps the only viable way in our lifetimes we will travel to another star. As I said, these space lasers could accelerate that tiny little spacecraft up to 20% of the speed of light, and at that speed it takes 20 years to get to the nearest star. You have to wait a little bit longer than that, because the nearest star is 4 light years away. And what that means is it takes 20 years for the spacecraft to get there, and then when it takes that photo and beams it back to us using radio waves, it takes another 4 years for the signal to get back to us. But from launch to getting the picture is about 24 years. So that's not too bad. Hopefully most of us will be around in 24 years and you'd actually get to see the results. So are we ready to do this? Well, not quite. There's a bunch of different problems to solve, like building giant space lasers. But probably the biggest challenge is in having that tiny little probe. And there is work going on this. This is called a femtosatellite because we already had microsatellites and nanosatellites, so we had to go down to femtosatellites. This is a real satellite. It's called KickSat. It's about 3 centimeters across, and it weighs 4 grams. And it has all the basics of a space probe on it. It has solar power, it has a few probes to measure whatever it's flying past, and it has antennas to transmit its signal back to Earth. Now, this is still not something that would be suitable for breakthrough starshot. All these electronics are exposed. If you shone a space laser onto this, it would melt. But if you could develop something that was even smaller, maybe 10 times smaller, and which somehow had the power to, with a tiny little antenna, to transmit its signal from 40 trillion kilometers away, and take a photo and all the rest of it, then you might actually have the sort of mini satellite that could be part of this experiment. But there are more problems to solve. And that's even if you got the space laser and you got your tiny little probe and you accelerate it up to the 20% of the speed of light, you have another problem. And that's that space is, despite its name, it's not space at all, space is not empty. The galaxy, the Milky Way, is full of dust. And when I say dust, I mean dust. I mean little grains of soot, little specks and flecks of junk. And you can see that in the night sky. If you go out on a dark night, you'll see the Milky Way, but you'll also see these dark patches. And these dark patches are dust clouds that are blocking out the light from beyond. You might say, well, you know, that's annoying. You don't want to fly into a dust cloud, but you know, there's lots of parts of the sky that don't have dust clouds. Well, that's not true. These are only the very densest, darkest clouds. But if you look in infrared vision, you can actually see that the dust is everywhere. So this is another look at the sky using a satellite called Planck that a bunch of Canadians were very heavily involved in, and you can see that there is dust over the entire sky. So everywhere you try and go in space, there is dust. Now, if I'm walking through space at these speeds, that dust isn't going to bother me at all. You know, I might get a bit of soot in my throat, or have to sort of wipe the soot off my forehead, but it's not a big deal. But if you're traveling at 20% of the speed of light, then every dust grain that hits you at 20% of the speed of light. And even a microscopic dust grain weighing a tiny fraction of a gram is a sledgehammer when it's traveling at 20% of the speed of light. So people have asked the question, well, what happens when you have a mini space probe traveling at this speed and you get hit with a dust grain? So I'm going to show you a highly technical, sophisticated calculation. This is the before shot, dust and spacecraft, and this is directly from the scientific paper. You get bad words like crater and molten matter. If this tiny little satellite gets hit by a dust grain, there's a fair chance that the satellite will get vaporized. So how do you get around this problem? Well, there's a few ways. One is you do not launch just one satellite with your space laser. They're tiny. Why not, don't launch one, launch 100,000 of them. So the idea is you'd have this huge cloud of these tiny little rice grain-sized spacecraft. And if 80 or 90% of them, 99% of them get knocked out by dust grains, it doesn't matter because you only need one to get to the nearest star. The other thing is you could put shielding around them. It makes them a bit heavier and a bit more complicated, but maybe the shielding will sort of slowly get blasted away by the dust grain and the spacecraft will survive. Or maybe you don't make them like square, you make them like a needle shape, and that way their cross-section to the dust is very, very small. So we haven't solved this problem yet, but people are thinking about it, and if you go back to that fantastic vision of all of these spaceships slamming into warp drive, maybe the reality is tiny little hair-sized space probes dodging dust grains as they zip over to the nearest star. All right, so why do we actually want to go to these other stars? Well, the answer, of course, is because we want to see if there are aliens there. We want to see if we are alone. This is the biggest question we can ask. It used to be a philosophical question, but incredibly, it's now a scientific question. Is there anybody else out there? And of course, if there is anyone else out there, we hope that they would be intelligent, and we hope that they would be friendly, like in E.T. or The Day the Earth Stood Still, and we really hope that they wouldn't be mean, like in War of the Worlds or in Independence Day. So we don't know. As far as we know, we have never found any life on any other planet anywhere except our own. And the reason why is because finding life elsewhere is really, really hard. Let's assume, it might not be a perfect assumption, but let's assume that if there is life out there, that it comes from a planet. And maybe there's life that isn't associated with planets, but our life's on a planet. So we have to find other planets. And that's really, really hard because planets are really, really faint, and even our biggest telescopes have trouble finding them. This is a very famous photo. It's called the pale blue dot. It was taken in 1990 by a spacecraft called Voyager 1 that, as it was about to leave the solar system, just turned back and just took one final photo back from where it came from. It's a photograph of the Earth from a distance of 6 billion kilometers. Can you see the Earth? It's that one little pixel right there. So that is the planet Earth, what it looks like from 6 billion kilometers away. So it's quite sobering to realize that every person who's ever born and died, every happy moment, every sad moment, every sports victory, every tragic loss, every piece of music ever written, everything that anyone has ever thought is important is all happening on that one little pixel right there. So that's pretty faint. You have to know exactly where to look to see it. And that's the Earth from the edge of our solar system. If you went to the nearest star and turned back and tried to take a photo of Earth, well, that's 6,000 times farther away. And a physical law called the inverse square law says that the brightness goes as the square of the distance. So if you try and take a photo from 6,000 times farther away, the Earth would be 40 million times fainter than that. So I don't have to work very hard to convince you that if you made that 40 million times fainter, you would not be able to see it. What's more, if you go from far away, then the sun is over there somewhere. But if you go farther away, then the sun and the Earth are right next to each other, and the sun is about 5 billion times brighter than the Earth. So put something 5 billion times brighter than the Earth there, and make that millions of times fainter, and you can see that it would just be absolutely impossible to see the Earth. So how do we find planets around other stars? There are a few cases where we can actually make pictures like this, and I'll show you one later. But the way we normally do it is a sneaky technique called the transit technique. And so these planets around other stars are called exoplanets, and we can't see them directly, but sometimes their orbit is aligned such that the planet drifts in front of its parent star relative to us. And when that happens, we can't see this, we never see this, we don't have the sharpness of vision to see this, but there's the planet, and it blocks out a tiny amount of light from the star, like less than 1%, but the star just gets dimmer for a few minutes. And then as the planet moves off the other side, the star gets brighter again. So we just measure the brightness of stars very, very carefully, look for little dips in their brightness that are happening at regular times, and that is a planet going around the other star. And that little dip carries an enormous amount of information, and we can actually work out the properties of these stars. So using this very simple technique, we have found thousands of these exoplanets. I looked up in the database this morning, the NASA database, and the current tally is 4,116 exoplanets that we know of around other stars. And the remarkable thing is that these planets are so different from our own solar system. So this is an animation showing you this is our own solar system. So the sun's here, Mercury's orbit, Venus, Earth, Mars, Jupiter, Saturn, and superimposed on that are just some of the other exoplanets that we know about. And you can see that their orbits, most of them are much tighter than ours, and they're all sorts of different ones. Some are going ridiculously fast, some are going slow, but they're all different, and most of them are much smaller than our solar system. So there's lots and lots of planets out there, and they all have very different properties from ours. So let's go back to science fiction for a moment and say, what does science fiction say? I mean, in lots of science fiction, there's a planet just like the Earth. It's very convenient, very cheap for filming purposes. This very planet looks like California. But of course, in some science fiction, there are planets that look nothing like the Earth. And so, here are a couple of my favorites. This is Mustafar, the planet at the end of Revenge of the Sith, where Obi-Wan Kenobi and Anakin Skywalker have a lightsaber battle on this lava planet. This, strictly speaking, is another planet. It's Earth, but it's very science fiction-y. Possibly one of the worst movies ever made, Kevin Costner in Waterworld, but he lives on a planet where global climate change has created a planet with no Earth, no land masses at all, just water. So, in science fiction we have lava planets and we have water planets. Is this science fiction or is this actually some basis in fact? Well, it turns out that there aren't a lot of planets out there that we've found yet that look much like the Earth, but we have found planets made of lava. And we have found planets that are completely made of water. These are not photographs, these are artist impressions, but our best understanding is that those are the properties of the stars. So, the Mustafar and Waterworld are real. There are really lava planets and water planets. But there are things that even science fiction hadn't dreamed up. One of the most common types of planet in the universe are these hot Jupiters. These are systems that have a planet like Jupiter, but they're super, super close to their parent star. They're like 10 times closer to the star than Mercury is to our sun. And instead of orbiting in months or in years, they orbit in days or even hours. And sometimes they're so close that the heat of the star is actually slowly evaporating the planet. We've actually found planets that appear to be made entirely of diamond. And perhaps one of the most common types of planets are these planets called super-Earths. They're planets that are perhaps about the same temperature as Earth and maybe have the same conditions, but they're much, much bigger. So here is Earth, and you get these planets that are sort of Earth-like, but 3 or 4 times the size. But what are the most common planets in the universe? The most common planets in the universe, as far as we know, are those that are in orbit around a particular type of star called a red dwarf. Red dwarfs, as the name suggests, are red and small, and they are the most common type of star in the universe. 70% of all the stars in the Milky Way are red dwarfs. You might say, well, that can't be right, because I walk out on a nice starry night and I don't just see all these red stars, and that's because they're so faint. Even though 70% of all the stars in the Milky Way are red dwarfs, there is not a single one you can see with your naked eye. They're everywhere. There's lots of them in our 20 of the 30 nearest stars to us are red dwarfs, and you can't see any of them with your naked eye. But these stars are very common, and they have planets going around them. And although they're quite dim and faint, and so you might think they might not produce much warmth, if you put a planet close enough to the red dwarf, it actually produces enough heat, enough light to perhaps make a planet livable and recognizable to us. So maybe this is the scene from a planet a bit like Earth, but orbiting a red dwarf. You've got oceans, you've got a shoreline, but everything is red. There's one way in which these planets will be very, very different from Earth, though, and that's that as far as we can tell, the planets that we're finding around red dwarfs are what we call tidally locked. That means that they always keep the same face towards their parent star. Now, we see this in our own solar system. The moon is tidally locked to the Earth. The moon always keeps the same face towards the Earth. The moon is a sphere and it has stuff on the front and the back, but you can go out always and see the moon and it always looks the same with the same craters and the same spots because it always keeps the same face towards the Earth. We never see the back of the moon. And so a planet orbiting a red dwarf would be tidally locked. So one side would always be facing the red dwarf and one side would always be pointing away. And so the conditions on a red dwarf would be very different from Earth. You never see a sunrise or a sunset. The star never moves. If you're standing in one place, the light would always just sit at one place, never moving in the sky. So it would always be eternal daylight or eternal darkness. This is the side in eternal darkness that's pointing away from the star, facing into space, and so this side of this planet would be unbelievably cold and perhaps uninhabitable, and depending on how close it is to the star, this side faced right above it, where the red dwarf is right ahead, might be very hot and unpleasant. And so there might only be sort of a narrow band here, which actually is livable. This way is too hot, this way is too cold, but there's going to be somewhere in a band on the red dwarf planet that might be just right. We've found these planets and we think they're tidally locked and maybe they look like this, but how do we actually know that these red dwarfs planets actually have life on them? And that gets really, really hard. The way we could do it is to look at the color of the planet, because what happens is that the molecules that correspond to life actually block out, swallow very specific shades of very specific colors. A more technical way of saying it is if you take a spectrum of one of these exoplanets, there'll be very specific colors missing. And if the right colors are missing, that would be the signature of life. And we call those signatures biosignatures. And here is sort of a simplified version of a spectrum. So this is the brightness of the planet versus color, going from indigo through to red. And this is how much signal you're getting. And so you can see that there are these particular places where the colors, particular shades, like this particular shade of red or this particular shade of green, are missing. And if the right shades are missing, that means that things like photosynthesis or methane or ozone are in the atmosphere of these planets, and to the best of our knowledge, those would be the signatures of life. So the goal is to make a spectrum, to look at the colors of that exoplanet very, very carefully and see the signatures of the molecules that might correspond to life. But this is really hard. This is sort of a simplified artist's impression. If you do a computer calculation, then a real spectrum might look like this. So you can see these dips, these missing colors, due to the molecules that might correspond to life. So that's sort of what it should look like. And if you take the world's very best telescopes and you use them for incredible amounts of time, you get something that looks like these black dots here. And you can see that this is pretty crude. It doesn't look anything like this. And you really don't want to say, oh, this little bump here is proof of life. It could be many, many different things. So we need bigger telescopes. We need to collect more data and get spectra to turn the quality of the data from this into this. And so astronomers are doing that. We're building telescopes both to go up into space and on the ground, the goal of which will be to look for these biosignatures. So one of those telescopes that will hopefully be launched next year is the James Webb Space Telescope, this enormous sort of successor of the Hubble Space Telescope that will have some capacity to look for biosignatures. And then on the ground, we're building these truly mammoth telescopes. This telescope is called the ELT, which of course stands for the Extremely Large Telescope. I'm not making that up. The mirror is 39 meters across. You can see cars here for scale. This thing is absolutely enormous, and it's being constructed right now, and it will be ready to go in about 2025, which is not that far away. And these are the telescopes that we hope will have the sensitivity to see perhaps the first biosignatures in the coming years. Now, you might be thinking, well, why are we putting all this effort into looking for life around these distant planets and around other stars? Because we've got all of these planets right here in our own solar system. Is there any life in our own solar system besides Earth? And the answer is maybe. We know that on Earth, water is important for most forms of life. So the first thing you might ask is there liquid water anywhere else on the solar system? And the answer is that on the surface of a planet or a moon, there's perhaps only one place where maybe there is liquid water, and that's Mars, and I'll come back to Mars in a moment. But underground, there's a whole heap of moons of other planets that have oceans underground. And the most spectacular one is Europa. Europa is a moon of Jupiter, and it, as far as we know, the entire planet is enveloped in an underground ocean. And while Europa is quite small, it's only a few thousand kilometers across, its oceans are unbelievably deep. So the average depth of the oceans on Earth is about 3.5 kilometers. The depths of the oceans in Europa are 60 to 150 kilometers deep. And what that means is that Europa actually has twice as much water on Europa than there is on all of Earth. So the place with the biggest oceans in the solar system is not Earth, it's Europa. We believe that that ocean is made of salty liquid water, and that's where life began on our Earth, in the oceans. And so perhaps, we don't know, but perhaps beneath the crust of Europa, there is life. This is just an imagination of what might be down there. We don't know because we haven't been to that ocean, but maybe there is life on Europa, maybe it's intelligent, but because it's beneath the surface, it doesn't know about us, and we don't know about it. We're very keen to find out more about Europa and the conditions in that, and so there are space missions being prepared that are going to go to Europa and check out more. One of them on the left here is this. These are both artist impressions. This is a European mission called JUICE, the Jupiter Icy Moons Explorer. It's going to be launched in 2022, and it will arrive at Europa in 2029. And this is a NASA mission, Europa Clipper. It's going to be launched in 2025 and arrive in 2030. And those are going to study Europa in great detail and try and understand the properties of the ocean and what's beneath the crust of Europa, and perhaps also send a probe down to drill down and see what's going on. We got a surprise about a year ago, much closer to home on Mars. The planet it's not a particularly hospitable planet, but it's the one that has the conditions closest to Earth. It's remarked every year around this time of year that there are many days in the year when it is warmer on Mars than it is in Waterloo. And recently the Curiosity rover found some rocks. It broke apart the rocks and found some what are called organic molecules, the sort of molecules that are produced as waste products by things like bacteria. So it found things like benzene and toluene and propane, these sort of molecules that at least on Earth are produced as a product of life. So it didn't actually find any bacteria. We don't know where those molecules came from, and maybe there's other ways to make them, but we have seen some evidence for these molecules on Mars, so maybe there is some very simple life on Mars. So here are all these ways of looking for life, biosignatures and molecules and the rest of it, but there's a much easier way. You can just shortcut all of these steps and just say, look, if there's an alien waving to us saying hello, then the answer is yes, there is life out there. And so another thing that scientists are doing is the search for extraterrestrial intelligence, or SETI, and this involves listening to the sky for radio signals, looking for an alien actually sending a message to us. So it might be Morse code, it might be just something very simple, it might be a piece of music, it might be a message, it might be a complicated broadcast, but scientists are using some of the biggest radio telescopes on the planet to search for signals. And this is an incredible needle in a haystack problem. You don't know which star is transmitting from, and you don't know when. Maybe the aliens only transmit for 1 hour every century. We don't know. So you're really just hoping for the best. And the other big thing is you don't know what frequency to listen to. If I went up to you and said, oh, check it out, there's this really good song on the radio right now, the first thing you're going to say to me is, which station? And if I say, I don't know, then you're going to have to go through every single station on the FM and AM dial looking for my song, and by the time you get there, perhaps the song is over. Well, that's the problem we have. We have no idea what station to listen to, so you have to cycle through every imaginable radio frequency searching for that signal. So far they haven't found anything. They're very transparent. They release all their results, and so far it's all just non-detections. There's an established international protocol. If they do find something, they will confirm it, and they will notify the United Nations and share all the data, so it won't be some sort of alien cover-up. But what might it look like at that moment? Well, in science fiction, it would look something like this. This is a fabulous movie, Contact, with Jodie Foster, all about the search for alien life. And while it's largely based on real life, Jodie Foster's character is based on a real person, Jill Tarter. This is the moment where she detects the alien signal. And we use supercomputers to look for the signal, but of course, because it's Hollywood, she's using a pair of headphones, listening to the radio signal. And the most ridiculous thing is, a few seconds after the scene, when she detects the signal, she whips out her walkie-talkie and starts yelling to the control room, asking them what's going on. These are the most sensitive radio telescopes ever built. The last thing you want to do when you're looking for aliens is to use a walkie-talkie. That signal from the walkie-talkie would completely drown out the signal from the aliens. So this is not how we would find it, but it would actually look something like this. This is indeed an extraterrestrial signal. This is the Voyager spacecraft, which has now left the solar system. And when they are setting up for each night to go alien hunting, the first thing they do is to make sure that they can detect Voyager. So yes, if there are aliens transmitting, you could see them. And unfortunately, except for Voyager, they've never seen another signal like this. Maybe the reason why we haven't found anything yet is because everyone around the galaxy is listening. Every alien is listening and no one is actually talking. And so people have thought about this and said, well, maybe we should talk a bit and see if anybody else can hear us. And this is called METI, Messaging to Extraterrestrial Intelligence. It's controversial. Some people say we shouldn't be transmitting. We shouldn't be saying to aliens, hey, we're here and we're super primitive and we don't have warp drive yet, because maybe they'll say, oh, that looks like a good planet to enslave. But people have transmitted messages. This is one of the first examples of METI. This was a signal sent from Puerto Rico in 1974. And because it was controversial, they decided to play it safe, and they beamed it to a star that's 25,000 light years away. So even if they get the message, and even if they respond straight away, we have 50,000 years before we have to worry about it. It's a very simple message. It shows you sort of what the telescope looks like, what humans look like. There's sort of a crude diagram of DNA here, and a bit of chemistry, and so on. It's a very basic picture. Here's another message. This was on 2 space probes that were launched in the 1970s called Pioneer. There's an actual plaque that was bolted to the spacecraft. These probes have left the solar system now, but maybe one day, millions of years from now, some alien will find them. So the equivalent of the old guy on the beach with a metal detector, some alien will find this thing and go, what is this? And they will look at this plaque and go, huh, they hadn't invented clothes. So this is the Pioneer. This is the Pioneer spacecraft. It's showing you how big humans are, men and women, relative to spacecraft. But controversially, and people now say maybe this was a mistake, this is a chart of the galaxy showing you how to find the sun. And if the aliens find the sun, it very helpfully says, well, now you found the sun, and here we are the 3rd planet. So it's really a map saying, come and invade us. The chances of these plaques ever being found is obviously incredibly small, but here is a message that's embedded on the Pioneer craft. The most recent space probe to leave the solar system was New Horizons. It flew past Pluto in 2015 and past an incredibly distant asteroid, Arrokoth, in 2019, is now heading out into the darkness. And to play it safe, it has a few stamps, it has some coins, maybe they're stamp collectors. I've always wanted one from the solar system. it has a bit of writing, a piece of a novel, which presumably the aliens won't understand, and it has the names of millions and millions of people who volunteered. It has their names engraved onto a DVD. But so we are sending out this stuff, and maybe one day, millions of years from now, aliens will actually find it. Okay, so I hope I've convinced you that even though we don't yet have warp drive and aliens, that the present and the near future are incredibly exciting. I am a little bit disappointed that we don't have our jetpacks and that we don't get to shoot horrible aliens with our laser guns. But when I step back and think about it, I think reality is still pretty amazing. As a comparison to sort of take away your disappointment that this is not 2020, even though we were promised in the 1970s that this is what it would look like. Here is an image taken by Canadian astronomers. And so I told you it's really hard to see directly planets around other stars, but you can do it. And this is incredible. Back in 1606 or something, I forget the exact year, Galileo looked at Jupiter through a telescope and he saw the moons of Jupiter going around Jupiter in real time. He saw a little mini solar system, the moons going around. Well, we can do that now with other stars. Here's an actual image of planets going around a star. And so this is the actual thing here from 2011 to 2016. We can actually see planets orbiting other stars. And even to me, if you would have told me 20 years ago we could do this, I'd say, no, that's science fiction, we can do it. But I think perhaps to me the thing that says we really are living in real-life science fiction is the fact that right now there is a 900-kilogram nuclear-powered robot that has a rock vaporizing laser traveling around Mars, and if we ask it to, it actually takes a selfie of itself. So I hope I've convinced you that, in the words of JBS Haldane, the universe is not only queerer than we suppose, but queerer than we can suppose. Thank you so much.
Awesome. That's good. You got to come on stage? Very good.
Thank you so much.
That was fantastic. Let's open the floor to questions. So the microphone is right there. You can just form a line if you have some questions. All right, you get going, and I'm going to look for online questions, and you win the race. You're first.
Hey there, so you mentioned that we're able to isolate and detect these exoplanets through transit signals, and you also mentioned the biosignatures that we can find off of them. So what's the process from going from this one little blip that we get in transit to finding an entire biosignature from that one little blip?
It's really hard. So what you can do is you can take a spectrum of the star when there's nothing going on, when the planet's not going in front of it, and then you take another spectrum of the star when the planet is going in front of it. And if you take the difference between those two spectra, the star goes away and you're left with the planet. But you've got to remember the planet is billions of times fainter than the star. So even the slightest error in the subtraction will completely wipe out the signal, plus the signal is really, really faint. So you have to stare not just at one blip, but hundreds of these blips over and over again and add them all up and slowly build up the signal. And even when you do that, the spectra are not very spectacular at the moment. So it's really just a case of gathering up huge amounts of light from these blips. You have to know exactly what time they're going to happen, and you have to get it over and over again. And it's hard, because suppose the blip happens every 8 hours, okay? So so you get one, say, at midnight, and you go, great, I've got that one. But the next one's at 8 a.m., the sun's up, you can't do that one. The next one's at 4 p.m., you can't do that one either. So often the periods of the blips don't even match up to when it's nighttime, and you miss out on a lot of them. So it's really, really hard work, and it requires not just a lot of scientific understanding, but incredible technical skill to get these very weak signals out of the data. So far, we have not detected one of these biosignatures. Our telescopes aren't big enough, but we've demonstrated the technology. There's a lot of world leaders of doing this technique right here in Canada, and once we have these new telescopes going, there's a very real chance that we'll be able to do this. The first detections will be really controversial, they'll be very marginal, and some people won't believe it. This is the way science works, but eventually there'll be one that's a little bit more convincing, and someone else will reproduce it with a different telescope, and then we'll see the same thing around a different star, and people will start to believe that we actually have detected these biosignatures.
Thank you so much.
Take another question in the theater.
Thank you for your talk. Aliens, Roswell, New Mexico, yes, no, maybe.
I think the short answer is no. I think you've seen how difficult it is to travel to other stars. If you are going to travel to Earth from a different star, why are you going to come all this way and then just sort of dissect a cow or something? You're going to do something more with it. Note that there used to be all these claims of aliens and strange lights in the sky, and then by the time someone else looked, it would be gone. Every person, in this continent now has, a phone that can take movies and all the rest of it. So if there were aliens making these strange visitations, there'd be, really convincing footage of it popping up on YouTube. Scientists with credibility would be seeing these things. None of that has happened. All of these claims have disappeared since everyone has a phone in their pocket. There's just no evidence this has ever happened, I'm afraid.
1948, no phones. Thank you.
Yeah.
Let me take one online, which feels like a nice physics question. Would the ion drive eventually turn positive after emitting negatively charged particles?
So it's emitting ions, which are positively charged particles, but that creates electrons. Electrons are much lighter, and they're just sort of discarded. So yes, by emitting ions, you're creating negative charge, but you just discard that, throw that out the window. That's a good question. Yeah, but the amount of fuel obviously slowly shrinks. So the NASA Dawn probe that I mentioned, it went through 400 kilograms of fuel in 11 years. So that's pretty good mileage. It took 11 years to burn through 400 kilograms of fuel. So it's incredibly fuel efficient, but as I said, really, really slow and gentle.
Perfect. Inside.
Hello, I'm Moni. I'm also a very big fan of science fictions. So actually two short questions. First one is, it didn't talk about parallel universe, how physics and physics, they look at the parallel universe. And the second one is, it's a bit funny because we have seen in the last 50 years, there were many rumors about UFO, Bermuda Triangle, and all that. But nowadays we don't hear anything like that. What's the reason for that?
So I think the answer to the second question is that people can't just, as I said before, people can't just say I saw a light anymore. If they saw something, they would have taken a photo of it, and everyone has a camera, and there's just nothing out there. It was easy to make things up when you didn't have to prove it. To answer to your first question, so the question is, what does physics have to say about parallel universes? Is that the question? So there's lots of great science fiction about parallel universes, some of which are very similar to ours and some of which are very different. It's controversial. Physics says that parallel universes can exist, but so far we haven't found any way to actually prove that that is happening. Quantum mechanics, which is a branch of physics that allows electronics to work, one interpretation of what quantum mechanics is that it's actually a continuous creation of new branching universes, something called the many worlds hypothesis. That's one interpretation of quantum mechanics. People have been arguing about this for decades, but so far we haven't had any way to prove it. There are some claims that you could actually see another universe bumping into ours by the faint glow in the sky called the cosmic microwave background, but none of this is really borne out. So it's valid physics, and people have conferences and write scientific articles about parallel universes all the time, but right now we don't have any way to test that, to know that they exist, let alone actually sort of look at them or jump between them.
Let's take one more in the theater, and then the remaining theater questions, you can get them after, and I have one online to finish up. So you're up.
Thank you very much. I'm just wondering, when you were talking about warp drive and different ways of traveling through space, and you mentioned things like, if we could go 20% the speed of light, and then you said if we could go 99% the speed of light. You never mentioned going the speed of light. So I guess I'm wondering, based on what we know now, is that possible? Is it possible to go multiple times the speed of light? And if so, what would it take to do that?
So the only way you can travel at the speed of light is as a light beam. So I did actually talk about traveling at the speed of light, though I didn't actually say it explicitly, and that's teleportation. If you break me up into information and transmit me in a radio wave, I'm essentially traveling at the speed of light. And so I could travel to a star that's 4 light years away in 4 years and then get reassembled at the other end, as long as you get around these minor problems of the amount of data and transmission speeds. But that is traveling at the speed of light. No actual object can ever travel at the speed of light. That's forbidden by the laws of physics. But information can travel at the speed of light. And indeed, every time you talk on your cell phone or listen to the radio, you are receiving information that has traveled to you at the speed of light. other question you asked is, can we travel faster than the speed of light? And the short answer to that is no. Like, the laws of physics forbid anything from traveling faster than the speed of light. If you use warp drive, then maybe you could drag space at faster than the speed of light, and at least that's what happens in Star Wars and Star Trek. That's not actually moving at all, it's just dragging space. So maybe that would be a way to effectively move faster than the speed of light. But all sorts of paradoxes happen if you can do this. You could actually travel back in time, and then you know the usual story of you could kill your grandfather, but if your grandfather's dead, then would you be born, and how could you do that? So I think the short answer is that all sorts of inconsistencies come up if you could work out a way to travel faster than the speed of light, and there might be clever exceptions to that rule, but as far as we know, the fastest you can travel is exactly the speed of light.
Thank you.
And let's take one last online question. What was your favorite sci-fi movie as a kid?
That's a great question. I know I can answer the movie what my favorite sci-fi movie as an adult, but as a kid, look, it's hard to go past the original Star Wars movie. I actually saw it at the drive-in, so I know that makes me probably pretty old. But you know, seeing that movie, I mean, the special effects of Star Wars were like nothing we had ever seen at the time. The story was amazing. The special effects, the baddies were the perfect villains, and the good guys were the perfect good guys. Like a lot of other people who grew up in the 70s, you know, Star Wars has completely shaped my thinking. Like, I wanted Star Wars, and you know, every research paper I write hopefully is one more step towards making that happen.
That sounds great. Ladies and gentlemen, Dr. Bryan Gaensler.
Thank you so much. Thank you, Greg.